Hi there. In this video, we're going to proceed with the lower part of glycolysis, and we're going to see phase 2 as we had described it. So far we have seen phase 1, okay, how we got from glucose 6 carbon units to 2 3 carbon units, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, which with a triose phosphate isomerase, this reaction, we now have glyceraldehyde 3-phosphate, which is the entry molecule for the lower phase of glycolysis. Before we go on, just to point out that in many textbooks you will see different sugars. We discussed glucose, but you will see how galactose, mannose, glycerol, and fructose enter glycolysis through this upper part. We will discuss this, but much later, okay, in before exam 3. I think it makes more sense then. So we'll get back to those sugars. Of course, glucose is not the only sugar we eat. I mean, we eat all of these sugars, and we need to understand how they get utilized, but we'll do it at a later point. So now it starts showing me the money. This is, we invested in phase 1. We spent 2 ATP per molecule of glucose. We haven't gotten anything out yet. Okay, so in phase 2, we're going to see how glyceraldehyde 3-phosphate will be oxidized, and the electrons will move on to NAD+ to give you NADH. And the product has a sufficient free energy now to drive actually ATP formation, right? So we're going to see 2 reactions. Okay, the oxidation of glyceraldehyde 3-phosphate to glycerate 1,3-bisphosphate, and then this high energy molecule, one of these phosphate, is a high energy phosphate bond, which could be directly transferred onto ADP and make ATP by the enzyme phosphoglycerate kinase to give you glycerate 3-phosphate, which then we'll see how that gets processed in phase 3 and get more ATP out of it before it becomes pyruvate. All these compounds for the remaining of glycolysis is going to be the lower part of glycolysis will be 3 carbon units. Okay? So no more breaking down of anything. Excuse me. So the first reaction, as I said, the one catalyzed by GAPTH, glyceraldehyde 3-phosphate dehydrogenase, is a redox reaction. So that's actually the very first redox reaction we're going to see. It deals with different redox states of carbon, oxidation states of carbon, and we have seen this before. Okay, these are fundamentally the redox reactions we're going to be dealing with. The oxidation states of carbon, the E value is shown here on the y-axis, very negative for the reduction of a carboxyl carbon. That's the most oxidized form to a carbonyl carbon. E value of around -500, -550. And then around -200, we have the reduction of a carbonyl carbon to a hydroxycarbon. That's a hydroxyl group here, which we have plenty, let's say, in sugars. And lastly, the one with a more positive E value is the full reduction of hydroxycarbon to a hydrocarbon. Okay. Now, in coupling these half cells, these are all half cells, half reactions. In making a complete full reaction, these are all reductions. Something has to be oxidized, and in coupling this, so picking 2 out of those 3 and coupling them together, something that's favorable always will tend to move more electron to whatever is already even more reduced. So in practical terms, that means that you pick something, let's say the blue one up there, which is the one that's more reduced, write that as a reduction. So you pick up a hydroxycarbon, you make it a hydrocarbon and couple it with any one of those 2 below it, that would be a favorable reaction. If you want to reduce, let's say, a carboxyl carbon and make it a carbonyl carbon, if you try to couple with an oxidation of any one of these things, it's not going to be thermodynamically favorable. Okay, so the easiest way to remember is that for favorable reactions, the rich tend to get richer. Now, you can make them happen if you spend energy in the form of ATP. But if you couple them right in the thermodynamically favorable reaction, as it turns out, to make ATP, you need about 250 millivolt change. Okay, delta A has to be a positive of 250, and that's enough energy to to actually drive ATP formation. And if you see how naturally they are spaced out, these carbon oxidation states, the half cells for carbon redox reactions here, they're nicely spaced so that if you can couple them favorably, you can get one in these cases, or if you go from here to here, you can get even 2 ATPs, right? So that's the point. So let's see. And that's the point I was making earlier, that the spacing between these oxidation states of carbon give you just about enough energy to make 1 ATP molecule. You can go in reverse if you spend 1 ATP, okay, for each step. And again, that's a favorable flow. The rich get richer. The unfavorable, you have to couple it to ATP. Hydrolysis. Now, we're going to introduce a color scheme because I think, and which we're going to use throughout the course actually, because it's quite helpful to underline the point, which underpins the point again that much of what we're going to talk about, the chemistry, is really based on the redox reactions and coupling these half cells. So this is glucose. Each ball is a carbon, okay, and the color of each ball represents the oxidation state of the carbon. Green, those are hydroxycarbons, okay? They have a hydroxyl group. Glucose is an aldose, so the aldehyde, the keto group, the carbonyl carbon, is found at the very end, and that's shown with yellow. It's more oxidized than the green ones, okay? Carbonyl carbons are more oxidized than hydroxycarbons. And these are the reactions we've seen so far, okay? In the first reaction, nothing happens, hexokinase will just phosphorylate the end. In the second reaction, isomerization here, we have nothing really. We convert the aldose to a ketose, so now we got fructose 6-phosphate. In the next reaction, again, PFK, we just add an extra phosphate at the very end. So you see, and finally with a aldolase, we clip it, and you know, with TPI, we convert the hydroxyacetone phosphate to glyceraldehyde 3-phosphate. So this is what we have so far. Okay. Now, with that scheme in mind, let's look at the GAP-TH reaction. This is glyceraldehyde 3-phosphate. That's the carbonyl group at the very end. And what's going to happen is this carbon, okay, which is a carbonyl carbon, is going to be oxidized. Ignore the phosphate at the moment, but that's a carboxyl carbon as far as oxidation state is concerned. All right. So the electrons, it's going to be this bond, the 2 electrons plus the proton, will move on to an AD plus and become an ADH. Okay. In the process, we'll also see how inorganic phosphate will actually be incorporated in this molecule. It's one of the very most ancient, reactions for ATP production. It's non-mitochondrial. Okay. It also has many moonlighting roles. In addition to this catalytic function, we'll see some other side roles that it has. So if we describe this in our color scheme, then, okay, so what we're going to have is we're going to convert the yellow, which is a carbonyl carbon, to a carboxyl carbon. That's oxidation, which also happens to be phosphorylated in this case. So now we are in a redox reaction. That's the type of enzymatic reaction, and it is this bond again that will be broken. So whenever you break a carbon-hydrogen bond, in principle, there are 3 ways that you can do this. You can split the electrons down the middle, okay, and you get what is called homolytic cleavage. So both the carbon and the proton each get 1 electron. But those are radicals and they're very unstable. And in living systems, it's not a good idea to generate radicals. The other way is to decide to have one of the atoms here picking both electrons. If the carbon picks up both electrons, it becomes a carbanion. Very common. Okay, we're going to see it in many different reactions later in the class. Or the other way is to generate a carbonium where the proton gets the 2 electrons. And in that case, you generate a hydride ion. Okay, so the carbonium for the carbon, and the hydrogen picks up the two electrons, and that's a hydride ion. And it turns out that this is how NAD or NADP dependent reactions work. Okay, they always the electrons move as a hydride. And so what happens to the hydride? There it is. It will attack the business part of NAD or NADP. Okay, and the electrons in the aromatic ring of the pyrimidine aromatic ring will bounce around onto the nitrogen, and you will get something like this, right? You know, when the electrons are donated, they will bounce back in exactly the reverse way of the arrows, you know, from here to here and this one here. And as a hydride again, it will go on to reduce something else. Right? So, but before we get to that, this is how GAPTH does it. There is a cysteine, so that's a sulfhydryl right there on the enzyme. Okay, it will attack, you know, the carbonyl carbon. Okay, so the electrons will bounce onto the oxygen of the double bond here will open up, and the electrons will go onto the oxygen, and you will end up with something like this. Okay, one carbon and a sulfur and an oxygen and a proton on the other end. Now, oops, let me move myself. So now this hydride, this bond will break, the carbon-hydrogen bond, and the proton and the two electrons as a hydride will do exactly what we described in the previous slide. Okay, they will be picked up by NAD+, okay, and you generate NADH, so in here. And now our carbon, if you notice how it is, okay, because the carbonyl carbon was reformed here, the oxidation state of this carbon has changed. If you imagine in the place of sulfur oxygen, which for redox purposes they are very similar, okay, what you really have here is a carboxyl carbon. You started with a carbonyl carbon, and you have an ester. It's just a thioester. It's not an oxygen ester, but it's a thioester. It's a carboxyl carbon for all practical purposes here. So this is where the carbon got oxidized, right? And the electrons moved on to NAD to become NADH. So this is the redox part, right? It also happens that this thioester is high energy, and a phosphate, just inorganic phosphate, will attack this carbon, and so that will enable you make this intermediate first, and now of course you can imagine the carbonyl will reform again, and the sulfhydryl will leave to regenerate the enzyme, and that is indeed what happens. And you have the product, you have the regenerate the enzyme, and you have the product, which is glycerate 1,3-bisphosphate. So we got our redox reaction, our carbon got oxidized, but we also got a high energy phosphate bond right there. So why does that happen? Again, because now that compound can drive ATP formation. And if you see the redox parts here, this is the only, I mean, our redox scheme with the color-coded scheme, this is the only, so far, the only yellow to red, the only carbonyl to carboxyl oxidation that we have seen in this scheme. And it so happens that this phosphate, as I said, is high energy and is interchangeable with ATP. Now, why this phosphate and not the other phosphate? If you notice, I have put them in different color here. You know, the backgrounds are different of the two phosphates to distinguish them. Well, so the pre-existing phosphate, the one that was put in by, you know, hexokinase or phosphofructokinase, they are low energy. Okay. That's a regular ester, but this one is an anhydride, the one that we just saw from GAPTH. And in reality, this is how they look. Okay, so it's only this one that's high energy, and it's only this one, this phosphate, that can be interchangeable with ATP. So why does it happen in this way and not any other way? I mean, this reaction, stay tuned. In a couple of videos, we'll see how all the reactions in glycolysis make sense. And that's actually the only way that is the best way to happen naturally, as you will find out. So maintain a little bit of suspense, but I will give you actually the answer why this is the best possible reaction to get what you want to get in this case. All right, before we close with GAPTH, it does have other, functions. Let's say it works here as a transcription factor again, okay, to drive histone transcription. And more keep coming up. it can initiate apoptosis, okay, and it goes in the nucleus and does all these things, which are independent. Apoptosis is programmed cell death, and these moonlighting roles are independent of the catalytic activity that we just described of the enzyme, okay? But it's typical of many abundant glycolytic enzymes that we have already seen. Almost every one of them has some moonlighting role. But back to glycolysis now. To complete phase 2 and to actually get some ATP back, we haven't gotten it yet, but now finally we're going to get it. So it's very simple. I told you the glycerate 1,3 bisphosphate. This phosphate is high energy. It's an anhydride, and the reaction is catalyzed by phosphoglycerate kinase, and it will move that phosphate will become the gamma phosphate in ATP. As you will see here, very, very simple. Let me move myself again. In this scheme, so ADP, sorry, will pick up this phosphate, become ATP, and what you get in the end is a glycerate 3-phosphate. Okay. So what do we achieve? I mean, what's this reaction? It's a group transfer, phosphoryl transfer reaction. We've seen them before, so we're not going to do this again. How? As we discussed previously. Why? Because it makes ATP. Very simple. There are two reasons, actually. An important one is it makes ATP. Okay, so this is an example of substrate level phosphorylation. All these principles that we had discussed in the introduction, how phosphates, how cells would like to do to capture the free energy of the food they consume, in this case, glucose, in little baby steps. The energy currency is ATP. The high energy phosphate bonds are really where this is the energy money that the cell uses, and they endow wherever they are found. In this case, on these molecules of glycerate 1,3 bisphosphate, they endow this molecule with enough energy to actually make ATP. Right? In addition, glycolytic intermediates, especially in the lower part of glycolysis, are extremely important building blocks for biosynthesis. Okay, so it turns out that 3-phosphoglycerate, this one, is a key building block for making, let's say, amino acids, in particular serine. Very important, and we'll come back to that later in the class. So yes, we're focused on ATP production here, but another major role of the lower part, especially of glycolysis, is to have these key 3 carbon unit intermediates for biosynthesis. So if we go back to our scheme of how the phosphor compounds, the high energy phosphometabolites again, are used in cells, we have ATP somewhere in the middle. This is the delta G under standard conditions. So is it really a high energy compound, the glycerate 1,3 bisphosphate? Yes. Okay, so it's the differential will be negative to make ATP. So you need to be above ATP, let's say, to be able to drive ATP synthesis in this case. And a lot of work was put into setting up this reaction, as we saw all the previous reactions in glycolysis, but it worked. And by the way, you get 1 ATP from each molecule of glyceraldehyde 3-phosphate. So, but 1 glucose will give you 2 glyceraldehyde 3-phosphates. So you will recover now 2 ATPs. The 2 ATPs that you spent in the upper part of glycolysis in phase 1, you have recovered your investment. You haven't made anything extra yet, okay, but you have at least gotten back what you put in. So energetically speaking, now it's all clean, but we need to make a little more, and the cell actually will make 2 more ATPs, okay, with the next phase in glycolysis, and we have another high energy phosphor compound here, phosphoenol pyruvate. It's even higher. The differential between ATP is even higher with phosphoenol pyruvate compared to what it was with glycerate 1,3 bisphosphate. So, but we'll see that in the next phase. So finally, to close here, we'll see where are we with our color scheme. Again, we start from glucose. This is glyceraldehyde 3-phosphate. It got oxidized with GAPTH. The high energy phosphate was transferred to ATP to make ATP, and now we are at 3-phosphoglycerate, which again, we have the oxidized carbon. So we'll close at this point, and with the next video, we're gonna finally complete the reaction of glycolysis down to pyruvate.